So last but not least, let's look at a principal component analysis, a PCA example, and let's do this example on a set of landmarks from a human face. So let's say, we have face photographs and somebody has gone painstakingly and clicked many points, maybe the tip of the nose, the top of the nose, and distributed 4 points along the way, the left eyebrow, or I guess the right one, the left one, and similarly the face contour, many points along the face, along the mouth, etc. And let's say we have 68 of these landmark points. Of course, each of these landmark points is defined by an x-coordinate and a y-coordinate on a plane. So let's say we have our origin here. This would have x1 and y1, etc. x2, y2. Let's say we have 68 of these pairs of points. So here is a snapshot of the data we used, and this is a data from a single person. Maybe the person is talking, so we have 20 frames of this person that is doing different things at different times along this video, and we repeat this landmark extraction, so we have 20 face images of a single subject. So for each of these images, we detect and extract 68 pairs of facial landmarks. And we would like to then analyze these, organize this 68 into a 136 dimensional vector. Again, we have x and y coordinates, so this is why it's twice the number. And so we organize each data point like this. Now we are talking about f as opposed to x in our previous videos for the derivation. So every time you saw f, you see f here, you should think of x, right? And of course, we can compute the mean of this data set as before. The PCA procedure involves centering the data, or it's subtracting the data from the mean, and then computing the covariance matrix, and then compute the eigendecomposition of this covariance matrix, and those are your principal components, right? So we first take your data matrix. We select this. This used to be our capital F here, X, now called capital F, and we first compute the mean and subtract the mean from the data, and then we compute the covariance matrix of this data, right, which is given as this. We then take the eigenvector and eigenvalue decomposition of this covariance matrix, and we compute the eigenvectors, and these eigenvectors essentially then become our model for the data, right? So if we have our mean vector, we can then go some step, which we call alpha, along the direction of VI, right? So starting from the mean of our data set, which is the mean face, right? So here's our mean. We can go some amount along the direction of xi, either in the positive direction or the negative direction. So if we go a little bit towards the positive one, you see this. If we go a little bit towards the negative one, you see that, right? And basically the person is talking, so not much is happening except you can see the variations here present in the mouth. Right. Here's the first component. So we have, however many data points here we have as far as principal components. So here's the first variation. Here's the second variation, right? So in the second variation, the mouth open is even higher, right? And you can see a little bit of variations along the eyes as well being computed. And here are some other principal components, and as you can see, basically, they're small variations, mostly around the mouth, and each of the principal components, also has an order of decreasing variance, right? So the most of the variance is contained in the first principal component, and then the second, third, and so on have decreasing variance as proposed earlier, right? So the code that implements this was done by Yan Zhuang. We load this data set, take 20 faces, compute the means, subtract the means for each of these. Subtraction is done here, right? And then we compute the covariance matrix, which is this outer product matrix here, divide by n, do the eigendecomposition, sort them in decreasing order as we have done, and then starting from the mean, add some amount of the standard deviation along that direction, along that particular direction, and add it to the mean, and this is the code that plots it. And so this is a very quick overview of the application of the principal component analysis technique.